Okay, I suppose we can start now. And in case people are joining, they're anyway more than welcome to join midway. So, I welcome you all to this problem solving and live interaction session for week 3. Good evening. Uh, uh, Before we proceed, I'd like to introduce myself to the people who are joining new. My name is Ganesh Ramaswamy. I'm a PhD scholar. I'm pursuing PhD in the Department of Applied Mechanics under the guidance of Professor K. Ramesh, who also happens to be offering this engineering mechanics course on the Swayam portal. And my co-guide is Professor U. Saravanan from the Civil Engineering Department. So the idea behind this session, as we have conducted 2 sessions in the last weeks, is that we will be solving some problems, and then whatever doubts that stem out of those problems, I will try to answer them. I would urge you all to solve it along with me so that whatever doubts you get, you can right away ask and get it clarified. In addition to this, there is also a forum. If you are not aware of that, on the Swayam portal, when you go, you can see a tab called Ask a Question. If you click there, it will take you to a Google group which you can join. Many people get their doubts clarified there also. So, in case you are more than welcome to ask the doubts here. In case you are not able to attend this session or for any other reason you get a doubt later, you are more than welcome to ask it in the forum also. We will answer it there. And midway through this session, we will have some. I'll just create a Google poll just to keep it a little interactive and participative. There'll be some multiple choice questions which I can show on the screen and possibly ask you to. There will be a Google poll on the right side. There is an activities button with a triangle, square, and a circle. So you can just click there when the poll is live, and you can report your answers. Which one do you think is right? A, B, C, D. So it is just to keep it interactive, and based on the answers, if I feel that there is any deficiency in the understanding, I'll try to address that and explain further. So with this, I suppose we can get started for the day. So the topic under discussion today for week 3 is trusses. So let us look at the first problem. So consider a planar truss loaded as shown. So we have been given a planar truss where the loads have been applied as shown and the dimensions have also been given. So we have been asked to report the values. This is something we need to take note of. If whatever answer we are getting, in case it is compression, we need to report it with a negative sign in the front. And if it is tension, we need to report the positive value that we are getting. So they have asked what is the magnitude of the net reaction at support C. This is support C. And then what is the magnitude of net reaction support A. And then they have asked two forces. So if we were to solve this, the first step towards this in rigid body mechanics is we need to remove the supports and replace them with the support reactions. So if we see reaction at C, we can see that this is a hinged joint, hinged end. This is a hinge. So basically this will offer translational arrest in both the directions. So this will basically offer reactions this way. The direction doesn't matter. It can be pointing from left to the right also. That will get corrected based on our mathematical analysis. But the essence here is that a hinge joint provides two restraints. That is, it doesn't allow the joint to move horizontally or vertically. Whereas the roller support at A, if we see, these circles indicate rollers. So basically it can move on that plane. The assumption here, in the underlying assumption here is that the rollers are smooth. There is no friction involved as of now. So it will only arrest vertical movement. So there will be only one reaction that the roller support would offer, whereas a hinge would offer two reactions. Going forward, we will see in beams that there is a fixed fixed support, clamped support, or as they call it. It will also arrest a moment. That is, it will provide a moment by arresting the rotation. Rotation also will not be allowed, whereas rotation is allowed in these two types of joints. So with that, if we were to, I will just replace them here itself. Let me take a force like this. Let us say this is, and first, most importantly, let me draw a coordinate system. Let us represent this by x, this by y. And as we have seen, x cross y is z, that will come out of the plane of the paper, out of the plane of the screen as you are seeing it. So right-handed coordinate system is what we are following. So there is a vertical reaction at C, let us call it Cy, because it is in the y direction. And there is a horizontal reaction at C, let us call it Cx for now, C in the x direction. Similarly, as we discussed, we can see that at joint A, there will be a y alone. There will not be ax because it doesn't offer restraint in that direction. It is allowed to, it allows movement. So with this, now we have replaced, consider the entire truss to be replaced by forces alone. We have removed all external entities like hinged and roller supports, and we have replaced them with external forces, which are reactions in this case. Now, if we have to see this truss, we know that this is in equilibrium. This is not moving anywhere. So these forces AY, CY and CX would have to mobilize themselves such that equilibrium conditions are satisfied. What are the equilibrium conditions? As we saw last week, in a planar case, it is sigma fx equal to 0, summation of sigma along y equal to 0, then summation of moment about the axis which is pointing out of the plane, which will be z axis. So sigma z equals 0. Many times that z is dropped, we just say sigma m equal to 0. But the implication is that moment is uh, it is about the axis that is perpendicular to the plane in which the truss exists, truss and the loads exist. Okay, with that, now if we have to calculate the net reaction at C, so let us proceed with calculating AY, CY, CX like that. So let me go here. I'll just draw it quickly here. CY, I have CX, I have AY. Okay. Now if I have to apply sigma fx equals 0, we can see that there is a force at F which is pointing in the negative x direction. So what would this amount to? So minus 50. I am dropping the units as of now because the answer is anyway asked in kilonewtons. So we needn't convert as of now, but one should be careful that whatever answers we get, it should be consistent with the units. So minus 50. Is there any other horizontal force that we see other than minus 50 kilonewton applied at F? We can see that there is a force Cx that we have applied at C, which is also we have taken in the negative direction. So we can take that to be minus Cx. Nothing else is applied. So this has to be equated to 0 because there is no acceleration. So what does this come out to be? Cx comes out to be minus 50 kilonewton. What does this minus signify? It signifies that the direction which we assumed is indeed needs to be flipped. It is the opposite direction in which it needs to be applied. So to that end, we have got Cx equal to minus 50. I am not correcting that direction and as of now, so I am just considering it as minus 50. Okay, now I'll do the next one. Sigma Fy equals 0. Sum of all the vertical forces. What do we have? We have at A and C, we have two vertical forces which are pointing in the positive y direction. Remember, this was x, this was y, which we had taken. So positive y direction will be positive forces. And there is a downward force applied at B, which is minus 50. So if we were to write this, what would this come out to be? Plus AY plus CY minus 50 equals 0. Or AY plus CY equals 50 is what we get. Let us call this equation 1. Now there are two unknowns in this equation. So essentially we need one more. This is one equation. We need one more equation to solve for both the unknowns. That comes from the moment equilibrium. So if we were to take moment, let us say moment about z. I am dropping the z as of now. It is the z axis. And I am denoting it by some point. Moment taken at which point? I can take it at any point in space, because this truss is in equilibrium no matter where we sit and look at it. So for convenience, because we want to eliminate unknowns, we know that a point where a force is applied, R cross F is the moment applied at that force. For example, this is the point, let us say some point X, and we have a force applied at this point. Let us call this F. So if we have some other point where some force is applied, if we take moment at this X, the moment contribution due to this force does not enter the picture. Why? Because R cross F is 0. Why? Because R is 0. It is applied at that very point. This is a convenient way for us to take moment about points, thereby eliminating unknowns. For example, in this case, if we were to take moment at point C, so Cy and Cx will not contribute to any moment at point C, because R cross F is 0, because it is applied at that very point. Similarly, if we have to take moment at point A, Cy contribution will not come. Cx contribution will not, Cy contribution will come, Ay contribution will not come. Cx contribution will not come, although it is applied at C, because R and Cx are parallel. I hope that is clear. So let us take moment about C. Now, in this right-handed coordinate system, where we take all clockwise moments, clockwise couples have their axis pointing towards positive z. So all clockwise are considered negative, because all clockwise have their axis pointing in minus z. I'm sorry, I had said I meant anti-clockwise. All anti-clockwise couples, if we see, they have their axis pointing in the positive z direction. So all anti-clockwise moments will be positive, all clockwise moments will be negative. Okay, let us take it about point C. What will this come out to be? So AY creates a clockwise moment about point C. So this will be a negative contribution. So minus AY into, what is the distance between A and C? It is 20. And then we can see that the other forces will create a clockwise moment about point C. So we can conveniently take it to be positive. So if we were to consider the force applied at F, it will be 50 into, what is the vertical distance between F and C? That is 10, given over here, plus moment due to the force applied at B. It is again 50 into 10, this 10. And just for the sake of completeness, I'll just erase this. Just for the sake of completeness, I will write plus Cy 0 plus Cx 0 equals 0. Are there any other forces that we have not accounted for? We accounted for all the forces now. And we can see that these two contributions go to 0. So there is only one unknown. So we can simply solve this. What does this come out to be? Plus 15 to 10 plus 15 to 10 equals 0. This comes out to be 50. So Ay comes out to be plus 50 kilonewton. It is positive, implying that whatever direction we considered to start with is correct. So we have got one of the forces, one of the reactions. We have got another reaction over here. What is pending is Cy. From equation 1, we can see that Cy comes out to be 0. Why? Because it is 50 minus Ay, which comes out to be 0. Okay. So what is the magnitude is what is asked. What is the magnitude of reaction at support C? At support C, this is support C. We are having one Cy, we are having one Cx. This Cx came out to be minus 50. The Cy came out to be 0. Both are perpendicular to each other. So what will be the resultant? Net reaction means it is the resultant of the two. One contribution is 0, so naturally the resultant becomes 50. And magnitude is asked, so we have to report the positive absolute value. So it is 50 kilonewton. That is the answer to this question. Now if you have to go, what is the magnitude of net reaction support A? At support A, we saw AY, which came out to be 50. Is there any other reaction at support A? Because it is roller, there is no horizontal component. So this itself signifies the magnitude. So this is also 50 kilonewton. Okay. Okay. What is the third question? Here we can see that the third question is, what is the force in member ED? This member. This member is what we are talking about. What is the force in that member? Now here we can go ahead and solve this by, there are two methods called methods for truss analysis. One is using the method of joints and the other is method of sections. We'll see both of them in detail now, but to start with, we could either proceed through this question by solving it using the method of joints or the method of section, but there is a simpler way to go about. So if we were to solve it using the method of sections or the method of joints, we can go about doing that. But just for the sake of simplicity, we can consider something called zero force members. So what is a zero force member? It is a member that for a current, for a particular loading case, it does not carry any load. That is what is a zero force member. Now there are two ways to find out what zero force, which are the zero force member for a particular load combination. Now if a joint has two members that are connected and this joint is free of any load, then these two members are zero force members. They do not carry any force. And in case a joint which has three members, if it so happens that out of those three members, any two members are parallel to each other, then the third member will carry a zero force. So these are the two ways to find out which are the zero force members. Okay, so at joint D, if we see, we can see that there is no force applied at joint D. So in that case, we can simply conclude that since there are only two members emanating from joint D, that is ED and CD, these two are zero force members. So what is the force in the member ED is what is asked. We know that this is 0. Okay. The next question is, what is the force in member AB? This member is what is asked. So what is the force in that? Now we can go with that method of joints which we spoke about. That is, we will basically consider this portion alone. This left side portion of the cut we will consider and redraw it. Our convention will be, we will invariably start with taking the forces pointing away from the joints. For example, we have considered joint A here. So what is the member force that is applied here? Force in member AF. We will take it pointing away from joint A. And what is the other member? We have a force like this. Force in joint AB. This is also we are taking pointing away from the member. Are there any other forces that we have missed? Yes, because there is a reaction at point A, which we just calculated, which came out to be 50, which we need to account for, AY, which is 50 kilonewton. This angle, let us call it theta. What is this theta? We can see that this FB is 10, is given to be 10. AB is also given to be 10. So this theta will come out to be 45 because horizontal and vertical are equal. So theta is 45 degrees. Okay. Now at this joint, we can do sigma fx equal to 0, sigma fy equal to 0. Can we do sigma m equal to 0 at that joint? We can do, but it will not give us any productive result because it is a concurrent force system. As we discussed in the last session, concurrent force systems do not offer independent equations using moment equilibrium because it is a trivial equation, that is 0 equals 0 is what we get. It doesn't help us in any way because r cross f essentially is 0 because r is a 0 vector. Okay, now if we take sigma fx equals 0 here, what do we get? FAF cos 45 plus FAB equals 0. This is one equation. What is the second equation? Sigma Fy equals 0 if we get. We can see here that it will be FAF sin 45 plus AY equals 0. So FAF comes out to be minus 50 root 2. If we work it out, that is what we will get. Okay. So if we were to substitute that here, what will we get? Minus 50 root 2 by root 2 plus FAB equals 0. And finally FAB, we get it as 50 kilonewton. So this is the answer to this question, 50 kilonewton. This is how we apply the method of joints. Now, when to apply method of joint and when to apply method of sections is a call that we need to make. Now, this truss is pretty simple. We have only, if we were to call these panels, we have one panel here, we have two panel, second panel here, third panel here. Now there could be trusses which could be very long, and there could be number of panels like this, say 100 panels. If we were to proceed with method of joints essentially has a constraint that it gives only two equilibrium equations with which we can solve. So method of joints can be applied only at joints where there are only two members connected, which is why we have to proceed with either of the ends and then come forward solving. So if there was a panel which had there was a truss which had 100 panels, and if we are asked to find the force in the 54th panel, let us say, if we start off with method of joints, we have to start from one end, come along solving all the way to 54, 53, and then solving the 54th panel will give us the member forces. This is the inconvenience that we have with method of joints, which is where method of sections becomes very elegant and very useful, which we will see subsequently. So as for this question, this is what we have solved. So if there are any questions regarding this, I'm happy to take them now. If anybody has any questions about the question we solved, you are more than welcome to unmute and ask, or you can even type it in the chat box. Otherwise, we can move on to the next question. Okay, I take it that there are no doubts, so I'll move on to the next question. And as we had discussed, I'll just create a poll for this question, and you can just answer what you think is the correct answer to this problem, to this question on the screen. A, B, T. So I have launched the poll. So you can just see on the right side of your screen in the activities tab, you will just see the poll. So the question here is the maximum number of independent equilibrium equations available at a cut section when the method of sections is used for analyzing a planar truss. Is it 2? Is it 3? Is it 1? Is it 4? Is the question. So although I have not discussed method of sections, I can see that many of you are already familiar with it. So that's good. I'll explain it just for the sake of completeness. Okay, so I'll just end this poll. I take it that the people who have answered it correctly. So the thing is, in method of sections, basically, if we had a truss like that, let us say like that. and then it was supported with some condition. In method of sections, we take sections that cut through the members. This section will essentially artificially isolate the bodies, the truss into two segments separately. Fully, those have to be separated. And then we can analyze each of the sections individually. So we can see that when we cut more than two members, when we cut three members, we can see that this is not a concurrent force system. So in addition to method of joints, which offered us sigma fx equal to 0, sigma fy equal to 0, sigma m equals 0 also helps, is a non-trivial solution in the case of method of sections, because we are essentially cutting out and creating a force system that is non-concurrent, which is why we have three equilibrium equations that are available. If the same thing, if we say that we just cut these, this is also a section. Why not call it the method of section? Because essentially we have cut the section nonetheless, but we have only two forces which are concurrent. So this essentially waters down to method of joints only. So this shows method of joints is but a subset of method of sections. Okay, let us move on to the. Are there any questions regarding what we discussed now, or I can move on to the next question? We yes, that's a good question. The question is that there is generally a condition that we should cut only a section which cuts three members. Why not four members is the question. Why not four or five members is the question. So as this very question answers it. See, our purpose in truss analysis is to find out member forces. Now if we were to cut a section which has four members, now those four members, when we cut, we have four forces in those members. So we have four unknowns. But each section provides us only with three independent equilibrium equations. With three equations, how many unknowns you can solve for? Only three. This is the reason why we can cut a section like this. Like that, if we cut 4, 5, we have exposed five forces. But is that section helping us solve for all the five? Is the reason. So that is a very valid and good question. Why we are not able to cut more? It's not that we are not able to cut, but it doesn't help us. Using the principles of statics alone, using the equilibrium equations, we are not able to solve for more than for more than three members at a section, which is why we cut only three. The recommendation is we cut three. There are some exceptions where those three are violated. Those exceptions are covered in the lecture if you have seen it, where there will be two forces which are pointing towards each other. But those are very exceptional cases. In general, we cut only three sections, only three members with a section, because we are available. We have only three equilibrium equations at our disposal. Okay. Yeah. Okay. So the next question is, which of the following numbered members is or are in tension in the truss loaded as shown? So we have to report our answer in one particular fashion. Enter the answer in ascending order without spaces. Let us say if we get the answer that member number 6, member number 4 and member number 11 meet the criteria that has been asked in the question, we have to assemble that in, arrange that in alphabetical order and report it without spaces. 4611. This is what we will report as an answer if that is what these are the members that we identify. So before we actually address this question, we should understand what a pin and a member does. So if we see, this is what a truss member looks like. So we are able to see that this is a simple basic truss. So we have seen that we are able to insert pins into this link. Now if I just separate them out, I have a link which has two pins attached to the ends. Now if I were to separate that also out, I have a pin and I have a member. Now when it is loaded, this pin will be pulling the member, and in turn from Newton's third law, member will be pulling the pin. Both will reach some sort of equilibrium, and that is where it will stay. So this begs the question: what is the kind of force that we show in truss analysis? We have shown here that there is a force in the member which is pointing away from that joint. This is with respect to which reference? This is with respect to the member, or this is with respect to the pin? Is something we need to understand it very clearly. We need to understand very clearly in order to proceed. All in our truss analysis, when we say that we start by assuming the force to be pointing away from the member, what we are essentially saying is we are sitting at the pin and we are looking at the member. So let us say this is the cut section. There is a pin over here. Now I have separated out that pin and I have separated out that member. So this is the pin, and let us say this is the member with a hole over there. And let us consider this. We'll put the member here. Let us consider that this member is in tension. It is being pulled. When the member is in tension, it implies that the pin is pulling that member. So this is the force it is applying. The pin is applying. How this is distributed along the circumference is a subject of higher studies. We won't go into that now. I am just showing that the resultant force is being applied on the member which is pulling the member. Now an equal and opposite force is being applied. Sorry, not this way. In the opposite direction, the member is pulling that pin. This is actually the pin. This is solid. This is the pin. So when we take a joint in truss analysis, we show a joint by an open circle, and we have two members that are emanating out of that. And for analysis, we say that we assume the forces to be pointing away from the member. Our inherent assumption is that the members, to start with, the members are invariably in tension. Because tension, we have to report as tension generally comes as the sign convention comes out to be positive. Most of the cases we report positive tension, negative compression. So we don't want to deal with negative numbers too much. So this is our first assumption, that all members, we will consider the unknown member forces to start with to be pointing away from the joint. Away from the joint implies, if I were to consider this diagram which I have shown, this is essentially the force that we are showing on the joint. So if it is pointing away from the member, it implies that that member is taken to be in tension. Okay. There is another way to look at this. If I were to consider it from the members reference, if I take this member 1, I can see that this is the force that has been applied, and there is another force that has been applied. This is a joint, this is a joint. Now I cut out this portion and I see just this. So there would be equal and opposite forces at that section, which means the member is indeed in tension if we were to draw the free body diagram. So this is the implication of having forces pointing away from the joints to be considered as tension. With this background of understanding, if we were to approach this problem, which of the following numbered members are in tension in the truss loaded as shown? So we essentially have to count out how many members have members forces shown which are pointing away from the joint. If we were to ask, if we were asked about compression, we would be doing the other way around. Which are the members that have forces pointing towards the joints? So which are those? We can see that this is one. This is one. Member 3 is one. Then do we have any other ones? All are towards the joints. So our answer would have to be 1. Okay. So are there any questions regarding this? I hope this concept which we discussed is clear. If there are any questions, I'm happy to take the questions. You can also consider typing it in the chat box in case you have any questions, or unmute, or else we will proceed to the next problem. Yes, 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 yeah. Yes, general convention, because we generally take positive quantities, positive forces as tensile forces. So we don't want to deal with negative numbers much. So we take it everything from the pins reference frame. From the pins reference, we can see that a force that is applied away from that joint will create tension in the member. This is why we take it that unknown forces to start with. If we have to consider it, we will draw it away from, pointing away from the joint. Okay. Are there any other questions? Okay. If there are no further questions, then we'll move on to this question. So consider a planar truss loaded as shown. We have been given a planar truss with 5 members, and the joints have been named A, B, C, D accordingly. And we have been asked to find the enter the magnitude of force in the following members. Those members are A, B, C, D. All the 5 members is what is asked. And we have to take note of this, that we have been asked to enter the magnitude of the force. So even in our assignments and exams for this course, this fact has been understood, and only then the questions have been framed. So if we are, even if we get a negative value, if we have been asked to report the magnitude, we should report invariably the modulus of that. The magnitude cannot be negative, so that is what we are supposed to report. Whereas if we asked in dynamics, we will see that there are vector components which could be negative. If we are asked to report the components, report a vector component wise, then we need to report it with the sign, of course. First step in the truss analysis is whether we can reduce the force system by removing the zero force members. And point to be noted here is that we are not physically removing the zero force members from the truss. A truss could have zero force member for one particular load combination. Trusses are generally used in civil engineering. If we were to see that the vehicle is moving for some particular load point, for some particular configuration of that vehicle's movement, there will be members which will not carry any force. So those are zero force member only for that split second. Load combination was to change, then it is not necessary that that zero force member would still be carrying a zero force. It could start carrying load and participate in load sharing. So the idea here is not to remove zero force members from the truss altogether. For one particular combination of load, a member could be zero force member. It is not universally true. Okay. So at joint C, if we see, we have a joint C, we have force of 30 kilonewton that is applied. And as per our convention, we will take this to be pointing away from the joints. So we have FBC or FCB, howsoever you want to refer to it. And we have another force, FCD, this force. Now, as we discussed, that at a joint, if there are 3 forces and 2 of them happen to be parallel, then the third force invariably has to be 0. So we can see that FBC and 30 are parallel. So FCD has to be 0. So this is 0. We have solved it even before attempting to calculate the reactions. Okay. Now, can we see any other joint where this case holds? Not as of now. Okay, so we will replace the forces, the reactions, as we had done for the first problem. Let us call this AY. Before that, let me take the coordinate system X, Y, and Z is pointing out of the plane of the paper. Okay, so AY we have put, let us put AX also, since A is a hinged support. Now, if we were to consider roller at D, we know that it will offer only one reaction in the vertical direction. Okay, now we can only proceed by if we calculate these reactions. So let us calculate them. First we have Fx equals 0. So what will this equation give us? We have one horizontal force which is pointing in the positive x direction, Ax. Are there any other horizontal forces? We have a horizontal force at C that is pointing in the positive direction. So plus 30 equals 0. So Ax comes out to be minus 30 kilonewton. Minus again implying that the direction which we considered is needs to be reversed. Okay. Now Ay and dy are still unknown. Now we take sigma Fy equals 0. What is it that we get? Ay pointing upwards plus dy pointing upwards. Are there any other vertical forces? We have a vertical force applied at joint B which is pointing downwards. So it will be minus 20 equals 0. So one equation we have Ay plus dy equals 20. Let us call this first equation. Now the other one would be the third equation would come from moment equilibrium. Now as we saw that we can take moment conveniently about any point in space and this equilibrium should still hold. But if we were to take it at if we were to take moment at a particular support, then the contribution of that support reaction does not enter our equation. It makes things simpler for us. So we can take moment about either A or D. This is just for convenience. This is not a rule. We can take it about any point and still get, we will get another equation which will also have Ay and dy, and we can simultaneously solve those two equations. A better way to do it is if we take moment about one of the supports itself, that support reaction gets eliminated and we can quickly solve for the other one. That is the whole idea behind this. So if we are to take sigma moment, I take it at let us say point D. I can see that Ay would create a negative because it will create a clockwise couple which will be negative. So there is a minus contribution plus Ax. Ax we can see that it directly passes through point D. So it will not have any contribution. It is 0. To understand this, if we have to see, this is R of A with respect to D, and this is where we have applied Ax, let us say. So this is the what will be the moment? It will be R A with respect to D cross Ax. So this cross product comes out to be 0 because both are parallel. This is why we generally don't take its contribution. This is the background behind that. Okay. What else is there? Plus this 20 kilonewton which is applied. This will basically create a anti-clockwise moment. So anti-clockwise is positive into what is the distance? This has to be the distance that we need to consider. And we can see from geometry that this comes out to be 3. This is 6. This is 6. This is 3. So that the remaining portion comes out to be 3. Are there any other forces that we have not accounted for? Dy, but its contribution is 0 because it is applied at that very point. And then we have force applied at C, which will create a clockwise couple similar to Ay. So that will also be a negative contribution. It will be 30 into what is that distance? This is this 3 meters equals 0. We have accounted for all the forces. Now this essentially goes to 0. This essentially goes to 0. So we can simply solve for Ay directly. What does that come out to be? 6 plus 20 into 3 minus 30 into 3 equals 0. It comes out to be minus 5 kilonewton. minus again implying that our direction needs to be reversed. Okay, for now I will leave it as minus 5 without reversing the direction. From equation 1 we can see that dy can now be calculated from equation 1. So dy is nothing but 20 minus ay, but ay we saw that it is minus 5, so it is dy comes out to be 25 kilometer, and it comes out to be positive, which implies that the direction we have considered initially to start with is correct. So we have got these member forces. Now what remains is to calculate. We have got the reactions. Now what remains is to calculate the member forces. I'll just redraw the truss again here. This is 30. This is 20. This was 5 minus 5, so I am just drawing it downward. AX also we got it as minus 30, so we had considered it to the right. So now we will correct it and consider it to the left. I'm not drawing this to scale, which is why the arrow for 5 and arrow for 30 is of the same length, because of space constraints, but it needs to be understood clearly what the relative magnitudes are. dy has come out to be 25. This is A, B, C, D. This we have already solved for. This is 0 force. So if this is 0 force at joint D, we can see that FBD is equal to 30. That is, if I consider joint D, FBD, as we had done earlier, 30, and we write sigma fx equal to 0, we get minus FBD plus 30 equals 0, from where it follows this result, kilonewton. So we have solved for two of the member forces. This we have solved. Now considering the third force, the third joint, let us say we consider joint C. We have 25 Newton, 25 kilonewton applied this way. This is 0. CD is 0, so that doesn't appear in our calculations. Then to be F, BC. Then we have F, CA or AC, however you want to refer to it as. This angle, let us call it theta. We can see from the problem that this is 3, this vertical is 3, horizontal is also 3, so again theta is 45 degrees. Now at this joint we can write the equilibrium equation and solve for the unknowns. So if I were to write sigma fx equals 0, what will I get? Minus fbc cos 45 minus fca. Are there any other horizontal forces to account for? These are about all. So this is 0. So we get one relation from this. If we were to take sigma fy equals 0, we will get fbc sine 45 plus 25. FCA doesn't have a vertical component. So these are all the forces that need to be accounted for. So FBC comes out to be minus 25 root 2 kilonewton. But in the question we have been asked to report the magnitude. So magnitude of FBC is what we will report. It will be 25 root 2 kilonewton. Now if you were to consider this equation, which is, let us call it equation 1, or maybe let us call it equation 2 because we are already named 1. So it is given that minus FBC by root 2 equals FCA. And FBC we have, so it is minus 25 root 2 minus of minus 25 root 2 by root 2 equals FCA. So FCA comes out to be 25 kilometer. So we have solved for this, for this we know is to be 0, this only one member force remains now. At joint A, at joint A we have downward force of 5, the leftward force of 30. Again we take it away from the joint, so this is FAB, and we have FCA, AC, whatever we want to name it. Now there could be a confusion that at joint C we have got force to be 25, which we took it to be pointing this way. Now at the other joint, why is it pointing to the right? This is because the member is in tension. If at joint A also we would have applied the force applying pointing towards the joint, then the member cannot be in static equilibrium. It is getting pulled because both the forces are pulling it leftwards, which is why we need to reverse it. This is something we need to understand clearly. So FCA, and this has come out to be 25 kilonewton as we already know. This is 45 degrees. Now I can apply again the equilibrium equations. So for simplicity, I directly apply sigma Fy equals 0. I get FAB by root 2, that is cos the sine 45, minus 5 equals 0. So FAB comes out to be 5 root 2. And it is coming out to be positive, which implies that our direction is correct. So we have solved for all the forces that were asked, and we can report the magnitudes accordingly. So if there are any questions on this problem, you are welcome to ask. I'll be happy to answer them. You can either unmute and ask, or you can ask it in the chat box. I hope things are clear. So essentially, this is how we apply the method of joints and method of sections for solving the truss problems. We can also do one example regarding the method of sections. Perhaps I could take this example and try to solve for one of the forces, because what was asked was force in member AB, and ED was what was asked, which did not involve the method of sections. So if we were to consider the same truss, and if we have to calculate for the member force FE, let us say, we don't need to proceed from A starting then do method of joints. We can directly consider the force in FE. So let me just work that out once. I'll just redraw the truss. So we have the truss like this, and we have 50 applied here, 50 applied here, and we had already calculated the reactions. So this here there was only a horizontal reaction. So there was only a horizontal reaction here, which came out to be 50, which was applied in that direction. So let us apply it correctly. 50. Here there was no vertical. Sorry, there was only a vertical reaction, which came out to be AY was plus 50. So let me just copy this. and take it at the end so that you can solve it using the method of sections just for one force, one member force, so that it becomes clear. So all the dimensions that were given are 10. This is 50, this is 50, this is E, and this is F, I presume. D, E, F, E, F, perhaps. Let us take the naming to be this way for now. Now, if we have to solve for member force Fe, we can cut a section like this, and then we isolate its free body. So we will have it like that. This is how we have cut the section. So there will be forces pointing outwards from that section. This is force FBC. This is force FFC. This is force FFE. And whatever forces are externally applied on that cut section, we need to report them. What is applied over here? 50. Okay. So this is the cut section for the left portion alone. Now if we see, if we were to take moment about some any point, so it should hold that sigma m equals 0 will hold. But the thing is, can we cut down on our calculation? If we were to take moment about E, about this point E, then there will be contribution of force Fc, there will be contribution of force Bc also. Why? Because they are not passing through that point. So they have a non-zero R. Whereas if we were to take the moment about point C, we can clearly see that F, the force in this member, the diagonal member FC, and the force in member BC, both pass through the point C. So their moment contribution is 0. So we will have essentially only one non-zero moment contribution, which will be due to FFE, which is what we want to solve. So this is how we should select a joint which is convenient for us for quicker calculation. So taking moment about joint C, what will we get? From this free body we are supposed to take. We will have minus 20 contribution of this 50. It will create a clockwise moment which is negative, which is why that minus has come about. And then we will have plus 50, and we are taking about joint E. Okay, so this distance is 20 from the question we can see. Then contribution due to this force will be 50 into 10, because this is given to be 10. Then contribution due to this force will be plus 50 into 10. And are there any other contributions that we need to account for? FFE, FFC will have a 0 contribution. Similarly, FBC will have a 0 contribution. And then there will be only a negative contribution from minus FFE into 10 equals 0, because this will create a clockwise moment. So from here we can directly solve what is, we can see that it is 0. It comes out to be 0. So this is how the method of sections is to be applied in case member forces in midway of the truss is asked, and this is how we can do it conveniently. So if there are any questions, I'll be happy to take them now. I have discussed method of sections, method of joints, how to identify zero force members, how to understand the sign convention that we are using, that member forces pointing away from the joints indeed imply that the member is in tension. That I have explained in detail. And why method of joints only offers two equilibrium equations, and why method of sections offers three equilibrium equations. And as someone had also asked, why we should consider only cutting three members using a section, why not four, why not five? So That also we have seen as to why that is, because we can only solve for three unknowns because of three availability of three equations from statics. So this is all I have to offer for week 3 as of now. So if there are any questions, I'll be happy to answer them. Otherwise, as usual, we can meet next week, Friday at 6 o'clock, to discuss problems on beams. And in between, if you have any questions, you are more than welcome to ask it in the Swayam portal. You can just go to ask a question, and you can ask it in the forum. We'll be able to answer it there also if there are no further questions here. So, with that, if there are no further questions, I would rather. Yes, yes. Yeah. So the question is that generally we consider x, y. If we were to consider this, we will go by the right hand rule and say that x cross y is z, which is pointing outward in the direction of the thumb as per the right hand convention. Y only clockwise, anti-clockwise is taken as positive, and why it is not taken to be negative is the question. So there is another question. I'll come to that 1 minute. Why we do this is because if we were to go by the left-handed coordinate system, there will be lot of minus signs showing up. So in order to reduce the clutter by the right-handed coordinate system, we can reduce the number of negative quantities that come up. This is the reason why we. Yeah. Okay. And there is one question. Initially at E, three members were present. And let me go to that question. Initially at E, three members were present. Yes. When ED became a zero force member due to two joints and no force, then at E there will be only two members present and no load. So, can we consider force? Okay, so this is an interesting question. That is, we are time and again applying the concept, and we are by induction we are saying that all the member forces come out to be zero. That is a interesting question, but that is not the correct way to go about. First, we have seen that these two at joint D there was nothing applied. So the first point is we have identified a joint where only two members were connected, and we have concluded that those two are removed. Those two are removed for the analysis part. But at joint E, initially, we see the configuration that is initially there. We don't, after removing, we don't see a truss that is afresh like that. That is what you are trying to ask is, if the case was like this, if a truss were given like this and this joint was free of any load, then these two would be zero force member. So this, whatever we discussed regarding seeing a joint where only two member forces are there without a force, or there is a joint where three member forces are there where two are parallel. This needs to be applied only to the original configuration. After we deduce that some of the member forces are zero, we are not supposed to remove them from the truss and consider only the remnant truss to apply these concepts. It's a very valid doubt that people get, that by induction they keep on applying this, and ultimately they reach a position where there are only two members left and all member forces come out to be zero. So this is only to be applied to the initial original configuration that we have. Zero force conditions to be applied only on the original configuration. Okay, so okay, that is clear. Any other things that need to be discussed? Any other questions? So good, there were some enchanting questions today that we saw. I hope with this background you will be able to solve the questions from trusses easily. And if there are any doubts, you are more than welcome to ask them now or in the forum. So we can take it from there. Okay, so if there are no further questions, then we can consider ending this session now. Okay, so in that case, we'll call it a day and meet next Friday. So thank you all for joining. Okay, then thanks. We can meet next week. Hope you will join for discussing beams.